instead of true or false, you can return an integer from goal test. If the goal test returns a value greater than 0, this means that the number of violation is positive. Otherwise, when it returns 0, this means that all of the constraints are satisfied and you can stop. And the last, successor function. Successor function is important because by a successor function, we can decide about the next step of the searching process. But it is dependent on your decision. For example, you can use the next step randomly, or you can choose the next step with respect to some heuristic. For example, greatest degree, or the nearest neighbor. Yeah, there are some examples of the successor functions. When you define these parts, your constant satisfaction problem is clear for all of the words, and all of the algorithm can be used for solving this problem. Is there any question? No one? Yeah. What is the searching process? For the common problems in the searching attitude, we can define a path from a starting state to the goal state. For example, in the DFS, we have started from one part and check its neighbor and select one of them and try to select one of them, and again and again and again and again. The path is important. But for the constant satisfaction problem, is the path important or not? I think the path and the length of path is not important, because you asked me about the satisfaction of the constraint. If I guess the solution and I have no any algorithmic idea for solving the problem, but I can find the solution, it is enough for you, because you search to find a feasible solution, not a path to receive to the feasible solution. Because of that, as you see, I write in the satisfaction of all constraints. But how you select it, I don't know. It is not important for me. Just try to find a feasible solution. Because of that, the path is not important. This is a kind of identification problem, not a planning problem. For planning problem, we define a path to select a step by step to receive to the goal. This is a plan. But for identification, I identify it as a smartphone. Complete. The way of representation is not important. This is identified as a card. Complete. The path is not important. In the CSP, we face with identification problem. And when we try to check, for example, a DFS for checking the process, maybe the length of all of the paths are equal to assign the necessary values for the variables. Yeah, the length of tree in this example is equal to the number of variables. if you have n variables, the length of pass in your tree search is n. When the height is n, it is not important which of the branch is solution. I just need to the assignment of the values to the variables. It is a good example of the identification, assignment to the variables. As you see, CSP are specialized for identification problems. But identification problem is very, very different and contain many practical examples in AI. For example, for face recognition, for fingerprinting, yeah, there is very, very different kinds of the identification. But now we focus on the assignment of the values of the domain to the variables. Now, for solution process, if I say that I have a black box that contain a prediction process, and can know that the feasibility of the solution, is it enough for consent satisfaction problem? Thus, if you have a black box without any knowledge about the data structure, without any knowledge about the order of the variables, without any knowledge about the order of the members of the domain, you can choose black box for feasibility study, just for feasibility study. But the processing time for this implementation is very, very great. Instead, in the consent satisfaction problem, we try to define a strategy for selecting one variable, namely xi, yeah, and searching on its domain and comparing the values of the domain, which of the elements of the domain is better to assign to the xi, and assign the corresponding element to xi, and then by the goal procedure, we test the constraint. If all of the constraints satisfied, we stop. Otherwise, we improve the process, for example, by backtracking. And also, sometimes you can implement the goal test more intelligent, and it can return some allowable combinations of the values for the subset of the variables. For example, it say that these two regions are colored similarly. Change it to, for example, red and blue. It is a guidance, a more guidance that can be received from the goal test. It is an intelligent implementation of the goal test. By using this intelligence, we can propose some special algorithm with more power to solve the consent satisfaction problem. And we try it. The first one. The first example is map color. As you see, we have different regions, and with respect to each region, we define a color. And it is related to the graph coloring. Yeah. If you are familiar with graph coloring, you're faced with a similar problem in the graph, who try to color the nodes with different colors. And in that context, we have a famous theorem, four-color theorem, that indicates any planar graph or planar map. Planar graph means a graph that can be designed on a page without disconnecting the link. Without disconnecting. This is the meaning of the planar graph. In the four-color theorem, we can color any planar graph with at most four colors. This means that it is possible to color it with, for example, 4 or 3 or 2 or 1 color. And each of the adjacent nodes are colored differently. Because of that, we can get a relationship between the graph theory and artificial intelligence in this problem. This is another example. Job scheduling. Job scheduling is very important. It is possible to define some objective function. For example, you can say that I need to minimize the processing time. And also, you can face with this problem as a constant satisfaction problem. For the latter, you can use the important variables in your task. For example, machines is important. You can consider the variables as the machines. Or time slot is important. You can define the time slot for your problem. Or processor. You can define the variable instead of the processor instead of the variables. Yeah? This shows that a range of the problem can be implemented by CSP for solving the job scheduling problem. And for the goal, total completion time or make a span or tardiness can be used. If you try to optimize this problem, you need to solve some integer programming problems. Integer program problems contain many different algorithms. For example, branch and bound. Branch and bound is a powerful algorithm for integer programming. But when we ignore from the objective function, we can use constant satisfaction problem in this process, and by taking a backtracking algorithm, we can solve it very, very efficiently. But as you see, this problem is NP hard. What is the meaning of NP hard? No one? If an algorithm, if for a problem there is no algorithm with polynomial time complexity, we say to such problem as NP hard. For example, for solving a linear system AX equal to B, we have a polynomial algorithm. We have big O n power 3 algorithm for solving any linear system. This is a good example of polynomial time algorithm. But for job scheduling, if you need to check the relationship between all of the variables, you should check all parts of the tree, and the number of nodes in the tree is b power h, when b is the branching factor and h is the height of the tree. In the constant satisfaction problem, height is in the constant satisfaction problem, height of tree is equal to number of nodes, n. Yeah. The height of the tree is equal to number of nodes, and you try to check different values for any node. That means as much as the domain is extended, the number of branch of any node increases. For example, if the domain contains 3 elements, the branching factor is 3. For example, if you try to solve this Java scheduling problem, I ask you about the number of time period. You say that K. The complexity of this algorithm is K power n, because you need to decide about any variable. You have n variable, thus the tree contains n level, and in each level you select one option for any variable. The option belongs to a set of k elements. This means that k power n. K power n is a non-polynomial complexity. Because of that, we say that this is NP-hard complexity. NP-hard complexity. This is similar resource management in the operating system. In the operating system is a good example of the constant satisfaction problem, because the user on tasks need some resources, and the operating system should assign the needed resources to the task or users. There is no objective function. We have a constant satisfaction problem in the OS for allocating the different, for example, CPU or GPU or other devices or other resources. Now, return to the first example. The first example, as you see, contain different regions. We define this variable with respect to regions. For example, WA is assigned to this part, and NT is assigned to this part, and SA is assigned to this part. There are 7 variables with respect to these regions. And for the domain, we define it similarly. D equal to red, green, and blue for all of the variables. And the constraint. For presenting the constraint, we have 2 approaches. The first one, presenting the constraint as implicit manner. Implicit manner means you present some logical constraint. Logical constraint, for example, WA is not equal to NT. This means that if you assign red to WA, you can assign red to NT. Or you assign green to WA, you cannot assign green to NT. This is a logical constraint. Logical constraint is very, very compact, because different colors for any pair of the nodes is compressed in a single logical constraint. We can define the similar logical constraint, for example, for any pair of the nodes, for WA and Q, WA and NSW, WA and V, WA and SA, yeah? And the second approach is explicit. Explicit is trying to capture all of the real values. For example, WA and NT can assign with a pair of the colors, red and green, and also can be colored with red and blue, and red and green, and green and blue. You need to capture all of the things. When the problem is simple, the number of capturing is high. When the problem is more complex, the number of capturing is very, very, very high. And we cannot present all of the necessary capturing in our implementation. Because of that, implicit implementation is more effective for constraint satisfaction problem. And until end of semester, we try to present implicit constraint for CSP. And a solution is a set of the variable with acceptable values. For example, red is assigned to WA, green assigned to NT, blue assigned in SA, green assigned to Q, etc. We can define any complex constraint satisfaction problem similar to this one. And also, we can propose a constraint graph. A constraint graph is a transformation of the constraint satisfaction problem by usage of nodes and links or edges or arcs. For this kind of transformation, for any variable, you define a corresponding node. And with respect to any constraint, you try to define a link. For example, WA is a node or a region. As you see in the previous example, it is the neighbor of NT and SA. Now, in the constraint graph, we draw a link between WN and NT and WA and SA. Yeah? When we transform a constraint satisfaction problem into a constraint graph, we can use the great advantages of the graph theory in this part. For example, in the graph theory, we have many properties about the nodes or degree of nodes. Or also, we have some information about the components. For example, in this part, as you see, SA has the greatest degree. For selecting the color, it is better to select SA at the first. And the second nodes or neighbors of SA can be checked again. This is the property of degree. And also, for the composition of the graph into some components. For example, we have two components. The first component contains more nodes, and the second component contains a single node. We can define two parallel processors. One of them try to solve the first one, and the second try to solve the second one. Yeah, it improved the processing time by usage of two processors. Yeah. Also, we can use the clustering in the graph, the composition of the graph into the paths, into the tree. For example, this graph can be decomposed into a path, W, A, N, T, Q, N, S, W, V, S, A. Yeah? And based on this path decomposition or tree decomposition, we can propose some improvement in the searching algorithm. Yeah. But the constraint graph is limited because they just implement binary constraint. What is the meaning of binary? Binary constraint is a constraint containing at most two variables. Because any link connects two nodes. Any node is a variable. Thus, in the constraint graph, we can just implement a binary constraint between two variables. If the constraint contains, for example, 3 or 4 variables, it is not possible to implement in the graph because there is no way to implement a relationship between 4 variables in the graph. In the graph, just nodes and arcs is implemented. But when we can present a constraint graph, we try to follow because it improves the quality of algorithm. And no. The famous example of constraint satisfaction problem, N queen. N queen problem is one of the most important problems in the theory of algorithm and in the artificial intelligence, and many different searching algorithms in AI is checked on the N queen problem. As you see, in the N queen problem, we have N cross N chessboard and N queen, and we try to locate the queen in the chessboard such that any pair of the node does not threaten each other. Yeah. For example, they are not located in a shared row. They are not located in a shared column. They are not shared in a diagonal. Because of that, the goal test contains 3 loops. In the first loop, check the number of queens in the row. If the number of queens in any row is greater than 1, it returns false. The solution does not satisfy the constraint. If the same happens in the column, returns false. If the same happens in the diagonal, returns false. Because of that, we have 3 important loops in the goal test. Again, the heuristics such as minimum remaining values or forward checking is useful. Forward checking means we check that before assigning a value for a variable, we check that what happens if I assign v to variable x. We need to predict we need to check forward. Before implementation, we check the status. This is the meaning of forward checking. We discuss in detail. Don't worry about that. For solving DFS, now you can use any DFS algorithm because DFS algorithm check the validation. For example, for 8 queen, you can check the process, and this is the solution of the 4 queen. As you see, there is no repeated queen in any row and in any column, and there is no repeated queen in the diagonal. For mathematical implementation, we can use two-dimensional variables, xij. Xij is a cell with respect to row I and column j. It is assigned with 0 if there is no queen in the corresponding location, and is 1 if we located the queen in the corresponding I and j. For the constraint, please pay attention. The first one, we fixed row. For a fixed row, namely I, at most one queen can be assigned. Because of that, both of the xij and xik can be assigned 0. Both of them 0. Means there is no queen in xik and no queen in xik. But if assign 1 to one of them, the other should be 0. 1 the second, the first 0. 1 the first, the second 0. Yeah? This is for row I. Second, for column j, similarly. For column j, xij and xkj, both of them should be 0, or at most one of them is 1. This is implementation of this constraint. For the third, for the diagonal, xij and xi plus k and j plus k. They are located in a diagonal. Because of that, at most one of them can assign 1. The other is 0. Another definition of the diagonal elements, xij and xi plus k and j minus k. This is another example of the diagonal elements. Again, they should be defined with at most one, a single one. And also we can extend the different kinds of the diagonal. I represented just 2 representation, but it is possible to present 4 constraints for recognizing the diagonal. It is the first formulation. For constraint satisfaction problem, you can define different formulation, mathematical formulation. For example, this is another representation of the mathematical models. As you see, instead of two-dimensional variables, now I choose single dimension variable. Because if I decide about row 1, at most one of the cell is used for queen. Because of that, there is no necessary to say two dimensions. For example, for Q1, cell equal 2 is used for queen. Q1 equal to 2. There is no other queen in the corresponding row. Because of that, there is no necessary to use the second dimension. For row 2, Q2 equal to 4. It means that the cell equal to 4 is used for queen, etc. As you see, the dimension of such variables are 1 to n, different from previous. Compare with it. In the previous, I presented bidimensional variable and the domain contains 0 and 1. Now, I propose integer variable. This integer variable can accept 1, 2, 3 until n as the values. Because of that, the domain is integer numbers from 1 to n. And the constraint. The constraint can be implemented implicit or explicit. For implicit, I say that not treating Qi and Qj. It is a procedure. In this procedure, check 3 parts. No repeated queens in row, no repeated queens in the column, no repeated queens in the diagonal. For the row, it is solved because for any row, I consider just a single value. Because of that, the first loop is not necessary to follow. But for the column and diagonal, we need to check. For the diagonal, I check, is there any pair of the Q with similar values? For example, if Q1 is equal to 1 and Q3 is equal to 1, we return false from this procedure. But as you see, there is no repeated queen in this solution. Because of that, the first loop is not implemented. The second loop is very simply checked. And now, for checking the third, we need to check the diagonal elements. For example, if I'm here, the diagonal is this one, and this one. No other constraint is needed. Because of that, implementation of the implicit by logical constraint is very, very simple. But if you focus on the explicit constraint, for example, for Q1 and Q2, you should capture all of the things. For example, 1 and 3 is okay. Yeah, 1 and 3 is not on the same diagonal. 1 and 4 is okay because they are not located in a single diagonal. But capturing all of the situation is very, very hard. Because of that, we prefer to use the implicit implementation. Yeah? Is there a problem? Very good. And the last example. The last example is Sudoku. Sudoku is a famous game containing 9 to 9 cells. 9 to 9 cells, yeah, and We can divide this 9 to 9 grid into 9 3 to 3 subgrid. Yeah, this is subgrid, this is subgrid, this is subgrid, and we should fill the free cells with number 1 to 9 exactly once. The constraint is no repeated value in any row and no repeated value in any column and no repeated value for any subgrid. We have three kinds of the constraint. The first one checks the repetition of the values in the rows. If the value is repeated, returns false. The second, check the values in a column. The third one, check the values in a subgrid. To implement this part, again, we define the variables. Variables is used for free cells. Each open cell is used as the variable. The domain. The domain is the values from 1 to 9. And the constraint. Showing the constraint explicitly is very, very, very hard for this problem. But we can use implicit manner. We define three kinds of the constraints. The first one, containing the constraint, including no way for no 9 way for 9 column. Yeah. RDIF. RDIF is operator. Is operator that check the different values for all elements of the column. Yeah. It is a logical constraint. Second type, 9 way are different for each row. Again, for any row, take the values. If they are repeated, return false. Otherwise, returns true. And the last one, for a subgrid of 3 to 3, take all different. Again, false. Otherwise, there is no repeated element in the row, no repeated element in the column, no repeated element in subgrid, returns true. The Sudoku is solved. As you see, by the simplest way, we present mathematical model for constant satisfaction problem. For the next lecture, we try to solve this constant satisfaction problem by ordering on the variable, ordering on the domain, filtering some parts, and investigation of the relationship of the constraint and checking the consistency between the constraint. They are left to the next work. I'm ready to your question. Please ask me about your ambiguity about the constant satisfaction problem. But for the solution process, remember that backtracking algorithm is useful, but we need to improve the quality of backtracking in the next lecture. Any question? Any problem? Thank you, everyone. All of the